Okay, thank you very much for to all the participants for connecting. It's my pleasure to introduce Karina Navarro Gonzalez from Universidad de Sao Paulo. So Karina will talk about sharp estimates for the covering numbers of the Weierstrass fractal kernel. So Kari, you have 40 minutes, 45 minutes plus 5 minutes of questions. Okay, please start.
Okay, thank you. Good morning. My name is Karina. I am a doctoral student at the University of São Paulo, Brazil. I don't know speak very good English, but I hope everyone can understand me. I want to share with you some results obtaining with my advisor, Tyler Down and Douglas Azevedo. Okay, here I go. The presentation will have the following sequence: a brief introduction, some definition and properties of Weierstrass fractal kernel, a presentation of a reproducing kernel Hilbert space associated to Weierstrass fractal kernel, and estimates for the coding number of operator IW. Okay.
Karina, I think your presentation is not moving. Or
now?
Can you try?
Now that
No, it's not moving. Maybe you can stop. Maybe you can stop sharing, and you can try. You can start sharing again.
No.
Okay. Please share your screen again.
Wait. I'm sorry. Here.
Oh. I see now your table of contents. So now it's okay, Karina.
Okay. Thank you. Okay. Okay, come on. In 1872, Weierstrass presented a class of trigonometric series W as follows. These functions are fractal type, since they are continuous but nowhere differentiable. When A is between 0 and 1, it's clear that W is a continuous and bounding function. When A times B is greater than 1 more trace pi over 2. The next definitions. Okay, now we will need some definitions. Let I, the interval -1, 1. We consider W defined on the Cartesian product of I with I, real function. The Weierstrass fractal kernel is given by a relation of WAB in X. Okay, therefore W is equal to this series in terms of cosines. Okay. The next definition is let X be a non-empty set. A symmetric function K real is called a positive definite kernel if it satisfies that the finite double sums is greater than or equal to 0. Okay. This for all greater than or equal to 2. X1 is 2xn in X and C1, C2, Cn in R. Okay. This theorem tells us that whenever we have a positive definite kernel W that exceeds a unique Hilbert space of function on I, satisfied the following condition. Oh, okay, sorry. Here. Satisfying the following condition, okay? I1, the function belongs to HW for all cheese and I. R2, reproducing, okay, sorry. Sorry, here. Lemma 2-1, okay? I'm sorry. We have the W Weierstrass fractal kernel is a continuous and positive definite kernel. Okay, but why? Well, for a between 0 and 1, W converges uniformly, and this implies that W is a continuous kernel. It's also not difficult to see that W is a positive definite kernel. Okay. Furthermore, the Weierstrass fractal kernel is nowhere differentiable as expected. Why? Because the nowhere differentiability of WAB proved by Hardy implies that the partial derivatives of W do not exist, and then W is also nowhere differentiability. Okay. Now, this theorem tells us that whenever we have a positive kernel W, there exists a unique Hilbert space of functions on I, satisfying the following conditions. I1, the function belongs to HW for all cheese in I. R2, reproducing properties, the inner product of I with W is F. That is, here, reproduce the function F. And R3, the span of the set is dense to a space of HW. Okay. So, this space is called reproducing kernel Hilbert space. Here the question is, what is the reproducing kernel Hilbert space associated with the Weierstrass fractal kernel? Since we already know that it exists and is unique, the next theorem, the next theorem answers this question as follows. The reproducing kernel Hilbert space induced by the Weierstrass fractal kernel is this, okay? HW composed of this type of function where the sequence, okay, Cn, Dn belong to here, okay? With the following inner product. If F is this and G is this, so the inner product between F and G is given by the product of their coefficients, okay? And the proof, okay, why is it true? The idea of the proof is to check the three properties of the previous theorem, right? For the first property is enough to write W as follows. Here, this W, where Cn and Dn are defined in terms of sines and cosines, okay? Thus, a span of W is a subspace of HW. For the second property, it's enough to calculate the inner product between F and W. The last property of implies that a span of W is a dense space of HW. Why? Well, because if F belongs to HW is such that the inner product is 0 for every X in I, the producing property implies that F is 0. And property R2 and R3 is proof. Okay. Lemon. Let F a complex function given by this series for a complex sequence AN having the norm series of its element summable and the sequence Bn with positive elements such that Bn converges to infinity. Okay. If these two conditions are satisfied, and then F is nowhere differentiable. Okay. The result is all valid for the real part and the complex part of F. And very important because it helps us answer where the non-differentiability of the kernel carries over to the producing kernel Hilbert space. Okay. Okay. We can say that yes, the non-differentiability property of the kernel is carried densely to the producing kernel Hilbert space, as we show in this theorem. Consider F belong to HW with serious expansion like before. Okay. If these two limits are different of 0, then F nowhere differentiable. Okay. Moreover, H is the collection of functions in HW with the 4 and satisfying 5, then H is dense in HW. Okay. Okay. Coding number. Now we are going to define the coding number of the operator in terms of unit balls. Okay. So the coding number is the minimal number of balls of the metric space Y of radius epsilon that cover the image of the ball in X. Okay. Our main goal is to investigate the coding numbers of the embedding IW here. Okay. Okay. The following lemma offers us property that will be very useful to obtain estimates of the coding number. Okay. As we can see, a first step should be to calculate the norm of the operator. Okay. Proposition. The norm of the operator is given by the square root of the quotients. Okay. To prove this, we only need to use the Cauchy-Schwarz inequality and the producing property R2 to then find an element that's here. To then find an element that offends the upper bound. Okay. Similarly, the proof above, we can determine the norm operator of projection on orthogonal space. Here, U, V are this space. Okay. Thus, for F belong to HW, we have the compositions for F. Okay. Okay. And the norms of these operators, IWPNU, IWPNV, are calculated, okay? The idea of the proof is similar to the previous one, okay? Notation. Here, this symbol means weak equivalence when the limit of the f over g1 is 1, when epsilon approaches 0, okay? And this symbol means a strong equivalence when we have this inequality. Okay, we finally have an upper bound for the coding number given by 4 times these quotients, okay? The idea of the proof is to write IW as the sum of the two projections. And here, 1, 2 projections. Okay. Show that the coding number of IWP and V is 1 here. Okay. We use the property of coding number of lemma for 1. Okay. For lower bounds, we need the following lemma. Let X and I and Y to real any dimensional Hilbert space, and T an operator on this space. So we have a lower bounds in terms of the dimension of a space. Note that here the space has a finite dimension. Okay, this is important. We found that the coding number is bounded below by 2 times this quotient. Okay. Here, the technique here is to truncate the orthonormal basis of HW, okay, and consider an operator, okay, here, operator on the generated of this new truncated space, En, okay. This is a finite dimensional space, okay? To use previous lemma in some properties of coding numbers, okay? Here, for example. In previous lemma here. Okay, main result. The coding number of IW is equivalent, okay, equivalent to the square of the logarithm of 1 over epsilon, as epsilon approaches 0, okay. Now, to prove this theorem is enough to use the previous theorem about the upper and lower bound. Okay, so it's simple, the proof. Okay, here some reference. This paper we need for the ideas, the proof. Okay, thank you.
Okay, Kari, thank you very much for your presentation. It seems someone has questions for Karina. I have a question about myself, Karina. Can you show the last slide?
Yeah.
Yes, your main result. So you have this is a sharp result for the covering number, yes, of the operator. You say, and you give up the steps to undertake this estimation, yes, this estimate.
Yes.
And I know that you work in applied mathematics also. How you apply this kind of techniques in applied mathematics?
Okay, it had several applications in many branches of mathematics, in information theory, including machine learning. It plays central role, okay? But today, it seems pertinent to me to talk a little about its use within dynamic system in partial differential equation, for example. Suppose you have a problem modeled through a differential equation, and for each initial value condition, you will have a globally defined solution.
Okay.
If there is a set that attracts the solutions, a global attractor, okay? Use fractal dimension, which is given in terms of the covering number, okay? So use fractal dimension is finite. That by Maillet theory, this global attractor can be projected injectively onto Rn. So Rn, finite dimensional space, okay, which is very positive to know the dynamic of the problem that left in infinite dimensional space. Okay, this is not my research focus, but so is the idea.
But still the main result looks impressive because you have your operator IW and the domain is HW. This is a infinite dimensional Hilbert space, yes?
Yes.
And then you compute the covering number for this operator, IW. But the definition of this covering number is very geometric. Could you go to the definition of the covering number? Here. So you have two Banach spaces, you have the linear operator. I just am trying to understand very well the definition of this.
Okay.
Yes, but this looks like one geometric property of the operator, yes?
Yes.
We try to this is for any operator, yes? The operator don't need to be injective or nothing, yes? It's just any linear operator, and the spaces X and Y are arbitrary Banach spaces, yes?
Yes.
Okay. Always we have this covering. But then this covering number could be infinite, yes? In the case if the operator is not, if the operator is unbounded.
Right. Right.
So in your case, your operator
case,
is compact, yes? Your operator is of Hilbert-Schmidt.
It's compact, yes. So the covering number is finite.
Okay, that's great. That's all for on my side. More questions for Karina? Okay, if not, so thank you very much, Karina, for your talk, and we expect to have you in the next
thank you very much for allowing me to participate in these workshops.
Okay, thank you. So thank you very much.